Soon after the Big Bang, the universe was full of very hot, high-pressure plasma.
Such that the density fluctuations that are produced in the Big Bang, they oscillate backwards and forwards like sound waves.
400,000 years after the Big Bang,
The universe becomes sufficiently cold and these sound waves are frozen. These have propagated a huge distance equal to about 500 million light years. And it's this fundamental length scale that we set out to measure.
Professor Sean Cole was born in 1963, a time of space missions and Star Trek.
I had an interest in space and astronomy from a very early age. At school, I had a natural aptitude for maths and physics.
He opted to study physics at Oxford because he could do astronomy from the first year. He did his PhD at Cambridge and postdoc at UC Berkeley.
I like to study the big question of where did the universe come from? What's the density of the universe? What's its age? How do galaxies form in this big cosmos?
Sean Cole joined the University of Durham in 1991, becoming professor in 2005.
Perhaps the area where I've made the biggest contribution is in terms of modelling structure formation in cosmology. Structure forms in a hierarchical fashion. This is just a picture that I drew back in the 90s.
A merger tree.
We can then use that as the backbone for modelling galaxy formation. This is done with big supercomputers now to model that formation.
In 1994, at a conference in Edinburgh, Sean was roped into the breakthrough 2DF Galaxy Redshift survey that won the Shaw Prize this year.
A survey was done beforehand, optical imaging, so we know where all the galaxies are.
The 2DF survey involved over 30 scientists in Britain and Australia using the 4-metre Anglo-Australian telescope with a 2-degree field.
A robotic instrument that can place an optical fibre on each galaxy and take the light back to a spectrograph. We could get 400 galaxy spectra every hour or so. The 2DF Galaxy Redshift survey comprised 250,000 galaxy spectra. We can determine the redshifts of these galaxies and hence their distance away from us. And that enables us to build up a three-dimensional map of the galaxies. The critical thing is that galaxies are not just randomly distributed, they're distributed in large-scale structure, in filaments and walls.
By measuring that structure,
we were able to detect a length scale called the baryonic acoustic oscillation length scale, which is equal to sound speed in the early universe times the age of the universe when those waves stop propagating.
The amplitude of that is very hard to predict. It's a real progress in science.
Hey.
Excited, naturally, but it also seemed that not that many people would be interested. It was a very academic topic.
But BAOs have become more important
because they're a fundamental yardstick to do basically very large-scale surveying of the geometry of the universe, which in turn tells us about the expansion history of the universe. And the big question today is, what is driving the accelerating expansion of the universe?
Sean has been fantastic working with. He was certainly very much heavily involved in the analysis. He's been always very focused.
So Sean's a theoretician, so he did a lot of very careful work figuring out if we understood how we were measuring the properties of the galaxies across the sky.
And then move to the exciting results from a rock-solid basis. He has a really nice knack of when you tell him something stupid, he tells you very gently and calmly in a rational way that your idea is stupid, right?
He's very patient and very smart. He's one of the most outstanding scientists in the world. He seems to be very modest about what he has done.
He comes up with lots of great ideas and unusual ideas. It's very inspirational for a young postdoc.
Professor Sean respects your idea, so even if we are very young scientists.
He's very nice and very kind to everyone.
He works both on observational data and computational simulation data. It is very important to the development in cosmology and the galaxy evolution.
taking a mathematical model and seeing it work out in the data, logical order, I think, is what rewards me.
His life seems just as orderly.
I had no great plans, just opportunities seemed to arise. I got to the end of my school, people said you should apply to university. I got to the end of my degree, they said you should consider doing research, and I certainly believe if you take on a task, then you want to do it as best you can.
Sean from Lancashire met Maggie from Yorkshire on a skiing holiday in Andorra.
We went independently of each other. Sean actually sat next to me and my friend on the plane, and I was teasing her. I was laughing at what I was saying to her, and I was thinking, cheeky devil.
They met up again.
There wasn't enough snow, so we ended up going into a bar instead.
Got talking and so on, yes.
Back in England,
I was just finishing off my PhD.
I was nursing in Middlesex.
Then Sean spent 2 years working in California.
We had some very good holidays in the States.
We climbed up this mountain. Then we got to the top and he proposed to me. I made him wait until the morning until I decided whether I was going to marry him or not.
I think she was scared I was going to leave her up the mountain.
Settling in Durham, the couple has 2 kids, 21-year-old Hannah, currently studying media in Bournemouth, and Daniel, 15.
Let's go, one at a time.
Sean helped the kids with homework.
Yeah, he's very good with that.
But I don't really need help with it because it's quite easy. You know
Would you like to follow in your father's footsteps?
No. Because I'm more sort of chemistry, sort of orientated.
So at the moment, he's thinking about being a pyrotechnician.
So Daniel and I like going cycling and mountain biking.
My passion at the moment is the allotment.
What are you growing there?
Potatoes, cabbages, tomatoes, leeks, beetroots, beans.
She doesn't trust me to do the weeding though, because I might pull out the wrong thing.
Do you understand what he does?
No. I'm really proud of him, yeah. He does work hard, doesn't he, Dan? It's his passion. Well, he's always thinking about something.
Mainly what I did wrong the day before.
And looking ahead?
Certainly wanting to get involved in future projects that are going to constrain dark energy. And in fact, John Peacock and myself are in a collaboration with Daniel Eisenstein that may be doing this in the future.
Professor John Peacock of Edinburgh University took over the reins of the Anglo-Australian 2DF Galaxy Redshift Survey in 1999.
As chairman, your main task, of course, is to make sure that everybody feels involved and informed. On the whole, we were a very happy family. There were challenges. Well, one example was, I said, to make the survey work, you need an image of the sky with data taken on photographic plates. We realised after starting the survey, the depth of the photographs wasn't quite uniform, so that had to be recalibrated. Prior to the 2DF project, the biggest such survey had been about 12,000 galaxies, whereas we pushed that up to 250,000, so it was a huge leap forward for its day.
New Anglo-Australian surveys are underway.
Completed now a survey of close to 400,000 galaxies, going to much greater distances. We probably know the redshifts of something like 3 million galaxies. Between 2020 and 2025, approximately, we'll measure the redshifts for 25 million galaxies. Over the whole sky, there's maybe 100 billion galaxies. I could imagine a significant fraction of that could have been observed by the year 2050. There's a period in the history of science when you go from knowing nothing to your knowledge saturating. We're right on the cusp of that at the moment, so it's an immensely exciting time. These days, it's all on the computer.
For the 2DF survey,
mainly the observations were done between 1997 and about 2002. We released all the final data in 2003 and the final science results in 2005.
John has written a cosmology textbook and collaborated in 230 project papers.
These days, the world of cosmology is much bigger, so there are huge teams of people working on big survey projects. So I find myself these days going off into smaller projects where I feel I've actually left an imprint on the work.
The 2DF Galaxy Redshift Survey
wasn't the first to see the existence of large-scale structure, but what we were able to do was to measure it much more precisely.
Including the baryonic acoustic oscillations.
You reach a point in the early universe where the sound speed drops, the baryon affects it, it's frozen in a fixed pattern into the clustering of galaxies, and its length never changes after that.
This length scale is being used to measure accelerating cosmic expansion.
And the direct inference, if you believe that Einstein's theory of gravity is the correct one, is that there's this additional substance that permeates all of space, which has these anti-gravity properties, which has this name dark energy. By now everybody is convinced that either we have to change the theory of gravity or dark energy is a reality. We've all stood outside on a dark night and looked up and thought, what on earth is all this about? So it's a great thing about being a professional astronomer, to know that you're able to get paid to do something that everybody can feel the importance of.
But John Peacock, who was born in Dorset, England, of radio operator parents, started at Cambridge University intending to be a chemist.
I realised after a year that physics was much easier, so I dropped chemistry.
But after his undergrad studies,
many of the jobs on offer didn't seem so appealing.
So he stayed at Cambridge for a PhD in astronomy.
In astronomy, and particularly in cosmology, you have to bring so many pieces of physics together.
He started his postdoc in 1981 at the Royal Observatory in Edinburgh.
We're now seen as one of the world centres of extragalactic and cosmological research.
In 1998, Peacock was transferred to be a professor at the University of Edinburgh.
John is so impressive because he understands the data, the technology, but also theory, and he does the equations and the calculations himself. He just does everything.
These days, actually, the precision of the data is such that it's harder and harder to be able to write down a neat formula. And in the end, you just have to do a big computer simulation to get the exact answer.
His knowledge is vast. You can ask him about pretty much anything.
If John doesn't know it, probably no one's worked out yet.
You haven't, got to hope. He's quick with a joke.
Life is about trying to balance selfish pleasure of enjoying yourself and being nice to the people around you.
John's a very pleasant guy. He likes being host in his house. We have institute parties there.
He also has 50 clarinets at home.
Here's one that was made in about 1890. Here's one that's made up 100 years later. I like understanding how the engineers thought about how to make the thing work better. And also, I like restoring them, so it was covered in rust. Now, it can make music again.
John started on the clarinet in secondary school.
Anybody could be offered free instrument tuition. It's become a great love of my life.
John has played in hundreds of classical concerts. Through music, John, a student in Cambridge, met Heather, a nurse in London.
We used to go up to Cambridge to sing with John's friend.
Sit. Oh, good boy.
He was so funny, he threw me in the fountain. So it was the sense of humour.
That's how I show affection.
Yes.
She was, shall we say, straightforward and plain speaking.
John and Heather married in 1982. Their kids, Duncan, Imogen and Sophie, are in their 20s.
None of you went into the sciences.
I'm just not very good at maths. My skills are best placed elsewhere. Let's just say that.
So we've had long conversations about things, but I am not a scientist. So generally it's at a very low level.
I'm very proud of my dad for the achievements that he's made in his career, and I think it's wonderful.
So sometimes I bring home a pretty picture and I say, look at this. So what is it? And you start to explain and then you find there's nobody left.
Dad used to take us swimming, go play sports together, play in the garden, play instruments together.
A tradition in our family is to build dams, streams.
We do with me. I'd be more than happy to do that. I do it as a little child at heart.
Here, I can't do it.
Right. Edinburgh's always special to me. I want to move back here when I'm finished studying and live here the rest of my life.
I used to take you to nursery on the back of my bike, didn't I? That was great fun. If you cycle like I do, half an hour is enough time to get you from anywhere to anywhere. It offers everything that a civilized existence requires. I'm going to stay in Edinburgh for the rest of my life.
Apache Point Observatory, New Mexico. This telescope is the main workhorse of an ambitious project in the United States to make the biggest, most detailed three-dimensional map of the universe, the Sloan Digital Sky Survey, or SDSS.
It's a 2.5 meter telescope, one of the most powerful telescopes in the world. It's not one of the larger telescopes in the world. This telescope has actually detected some of the very furthest objects in the universe. What makes it so impressive is the very large field of view, the size of 36 full moons.
Harvard University astronomy professor Daniel Eisenstein is a co-winner of this year's Shaw Prize for leading a group of SDSS researchers to find a novel way to measure the distance and distribution of galaxies based on baryonic acoustic oscillations, sound waves that echoed in the early universe that provided astronomers with a cosmic ruler.
The sound waves get started at the Big Bang and they finish when the universe becomes neutral, about 400,000 years after the Big Bang. And in that period of time, they can travel a very particular distance. The universe has expanded since that time, so that distance is now much larger. But that distance is a very characteristic distance that we can test. We start with taking images of the sky.
The bright spots are lights from distant galaxies. Their positions in the sky are reproduced on this metal plate.
This is an example of one of the plates that we use in the Sloan Digital Sky Survey. So each hole here represents the location of where the light from a distant galaxy or star is going to fall when the telescope is pointed in just the right location. We've done about 6,000 of these individual plates. To each of these holes on the back side of the plate, we would plug a little optical fiber.
The plate with optic fibers is placed in this black cartridge.
It's mounted on the telescope.
The telescope turns at the exact location in the sky it had earlier photographed.
We're just going to sit there and stare at it for an hour. We're able to collect the light from many such points on the sky. Then enters into an optical fiber, which then travels off to our spectrographs.
The redshift of the light's wavelength is analyzed to calculate the distance and distribution of galaxies.
The spectroscopic data is allowing us to make a three-dimensional map. Maps usually have a scale on them that says, 1 centimeter equals 1 kilometer. And we don't have that scale. But once we find a characteristic pattern in the map, then we can infer the scale.
Daniel's study and the Anglo-Australian 2DF Redshift Survey both released findings in 2005 of the same pattern.
One of the key patterns that we're looking for is a signature of sound waves that propagated in the first 400,000 years after the Big Bang. A pond of water might be a way of visualizing this affects. If you drop the rock into the pond, that's the location that one galaxy will form at. But that rock then creates a wave which travels out, and where that wave ends, then that's going to preferentially create conditions for other galaxies to form. If we have one galaxy here, we are slightly more likely to have another galaxy 500 million light years away. We are able to use this 500 million light years distance as our meter stick. And then we can see them yet again, their imprint 10 billion years after the Big Bang. It gives this so much leverage. I just studied the expansion history of the universe. The expansion rate of the universe is accelerating today. We have no idea why this is happening. The name we give to it is dark energy. I sometimes joke that this overstates our knowledge by a factor of 2, because all we really know is that it's dark. We don't even know that it's really energy. So it really is, it's one of the great mysteries in physics today.
How did you get into astronomy?
I was very active and interested in mathematics and science in high school.
He majored in physics in Princeton University in 1992 and took his doctorate in astronomy at Harvard in 1996.
I actually came more from the physics and math side, and I only learned my astronomy rather late, really rather different entrance into the field. But I think that speaks to the breadth of the field, that it really is unifying mathematics, physics, astronomy, and computing, and statistics, and now even chemistry and biology.
Daniel now heads the third SDSS survey that began in 2008 and ends this year. It analyzed light from 1.5 million galaxies.
It's been an amazing few months.
First, he was elected to the prestigious U.S. National Academy of Science that advises the country on science and technology.
I was elected to the National Academy a few weeks before I received the news of the Shaw Prize, and then my second son was born 3 days ago. So it's in a 1 3-month period, there have been 3 major events. Right now, a lot of my focus is on family. So my first son is 3.5 years old, so that's been very occupying. You can see I have 5 hands, and so I juggle constantly. No, it's just, these are good problems to have.
He's always actually been phenomenal. I work closely with Daniel on the Sloan Digital Sky Survey. You know, he started as a theorist, but he became very observational and developed this, and that's usually a talent that most theorists never can't do, let alone do, and he does it with an exceptional quality. I've known Daniel for 10 years. He is a very understanding, very warm individual that really tries to understand that everyone has a different pace, everyone has a different ideas, and all of these are welcome at the table.
We do science to work on the questions that we know about now, and in the process of answering those questions, we hope to uncover the next generation of questions.
When scientists look at a cell with normal microscope, inside is quite simple. Only DNA containing nucleus, Golgi apparatus, and mitochondria. But after World War II, scientists looked at cell again with electron microscope. They are surprised to find cell containing many organelles.
One of the largest, the endoplasmic reticulum, or ER.
A folding compartment in which all the proteins have to be folded to be functional.
How this organelle works and its potential to cure cancer, Alzheimer's, diabetes, and other diseases remained a mystery until 2 scientists made a breakthrough discovery 20 years ago. Professor Peter Walter, University of California, San Francisco, and Professor Kazutoshi Mori, Kyoto University.
We figured out how it works. We know how we can manipulate it now, trying to see where things go wrong in diseases and what we could possibly do to fix them.
Maybe it takes 10 years. Drug development, it takes long times.
All right, Peter. Biochemistry professor Dr. Peter Walter out with staff from his laboratory on a Friday.
My second family. We're getting the lab together quite frequently.
Peter has around a dozen researchers.
People need to work in very confined spaces, and it's stressful work.
He's worked at the University of California in San Francisco for 30 years. 20 years of that have been devoted to studying the endoplasmic reticulum,
compartment in which protein folding takes place. Most people who think of proteins think of food, eggs, steak, but proteins are really the constituents that make a cell work.
Proteins do life-saving jobs in our body. They make insulin, strengthen muscles, and immunity to diseases.
If you look at this protein, for example, it folds up into this incredibly beautiful three-dimensional structure.
Peter studied bacterial cells of yeast to figure out how the ER regulates protein folding.
Assembly line is a very good analogy, in which all the proteins that have to be assembled.
Proteins enter the ER as a string of polypeptide and must fold into a 3D structure before they exit. If they misfold and clump together, they become toxic to the cell and cause diseases like cancer. Anytime unfolded proteins accumulate, the ER increases folding capacity by calling in more chaperones, the molecules that help them fold. But if the ER is overwhelmed by too much unfolded proteins, the cell goes into self-destruct mode.
So these are actual cells which we can watch under the microscope. And what we have here is two experiments. In one, we just watch the cells grow happily. Healthy, beautiful cells. Whereas the cells that have the unfolded protein response induced commit suicide and die by having too many unfolded proteins and not being able to fix the problem. Our main discovery is to find out what is the machinery that senses what's going on, whether the system is in equilibrium, whether the ER can handle the load of proteins entering it. Can I fix the problem, or should I rather die? And this sensing machinery is what we discovered. This molecule is called IAU1. It sits in the membrane of the endoplasmic reticulum. So you see the groove in the middle here, the binding site that sees the unfolded proteins. It senses how much unfolded protein do we have. We can watch it in the microscope, and you see that the IAU1 molecules start running together, forming these clusters in the membrane.
Peter believes the ER holds the key to curing cancer.
In cancer cells, for example, we would like to make the unfolded protein response more responsive to unfolded proteins, which are there in the cancer cells, that will activate a suicide program. That should be very broadly applicable to many different cancers.
That includes the cancer that struck Peter 5 years ago, now in remission.
I came home from a meeting in Europe one day, and Patricia gave me a hug and found this little bump on my neck. And a couple of days later, I had a diagnosis. There was a neck cancer.
He's very strong and with a long will to get well, and we went through.
Patricia is a retired science teacher.
We met in 1980. I had just moved recently to New York City.
At the time, Peter had just received his doctorate from New York's Rockefeller University.
He looked like a caveman.
Yeah, would you date a guy like that?
I am from Mexico, and I came as a graduate student here to the United States. I study in NYU. I got my PhD there. We have two girls, Sylvia and Gabriela.
So it used to be our garage, now it's my workshop. This is a sculpture I'm making for the garden. It's going to be a fountain. I actually keep very few of the pieces I make. Most of them I give away as gifts to other people. It's the act of making. The same as it is the act of discovering. It's not the discovery in the end that makes me happy, but it's the process of creating these pieces.
Peter grew up in Berlin.
My dad had a little chemist shop in Berlin. He was selling chemicals and household items. And I became fascinated with chemistry.
He majored in chemistry in Free University in Berlin and took his master's at Vanderbilt in the US.
Oh, Peter! Good to see you, man. Glad to see you.
Peter, everyone knows, is probably one of the world's best experimentalists. He's got an amazing talent to going into a problem, an unknown problem, finding exactly the right experiment to do and doing it beautifully. Then when he gets results and extracts gold out of it.
So what about inherited protein folding disease?
1990 is when I started in Peter's lab.
That influence the death pathway.
You choose the lab that you want to do your PhD thesis in. And my roommate had got these pamphlets and we went flipping through, and when we got to Peter's, we just laughed. It was like, but there's no way I'd work for him. Here's this guy with all this facial hair, and he was holding a little mouse, and he didn't even work at Mice at the time. The two of us said, oh, we'll never ever join Peter's lab, and blah, blah. But we rotated in his lab at the same time, because we were so compelled by the great science and what an awesome person Peter is.
Peter published his discovery in 1993, the same year as biochemistry professor Kazutoshi Mori of Kyoto University.
When scientists look at a cell with normal microscope, inside is quite simple. Only DNA containing nucleus, Golgi apparatus, and mitochondria. But after World War II, scientists looked at cell again with electron microscope. They are surprised to find cell containing many organelles.
One of the largest, the endoplasmic reticulum, or ER.
A folding compartment in which all the proteins that have to be folded to be functional.
How this organelle works and its potential to cure cancer, Alzheimer's, diabetes, and other diseases remained a mystery until two scientists made a breakthrough discovery 20 years ago. Professor Peter Walter, University of California, San Francisco, and Professor Kazutoshi Mori, Kyoto University.
We figured out how it works. We know how we can manipulate it now, trying to see where things go wrong in diseases and what we could possibly do to fix them.
Maybe it takes 10 years. Drug development, it takes long times.
All right, Peter. Biochemistry professor Dr. Peter Walter out with staff from his laboratory on a Friday.
My second family. We're getting the lab together quite frequently.
Peter has around a dozen researchers.
People need to work in very confined spaces, and it's stressful work.
He's worked at the University of California in San Francisco for 30 years. 20 years of that have been devoted to studying the endoplasmic reticulum,
compartment in which protein folding takes place. Most people who think of proteins think of food, eggs, steak, but proteins are really the constituents that make a cell work.
Proteins do life-saving jobs in our body. They make insulin, strengthen muscles, and immunity to diseases.
If you look at this protein, for example, it folds up into this incredibly beautiful three-dimensional structure.
Peter studied bacterial cells of yeast to figure out how the ER regulates protein folding.
Assembly line is a very good analogy, in which all the proteins that have to be assembled.
Proteins enter the ER as a string of polypeptide and must fold into a 3D structure before they exit. If they misfold and clump together, they become toxic to the cell and cause diseases like cancer. Anytime unfolded proteins accumulate, the ER increases folding capacity by calling in more chaperones, the molecules that help them fold. But if the ER is overwhelmed by too much unfolded proteins, the cell goes into self-destruct mode.
So these are actual cells which we can watch under the microscope. And what we have here is two experiments. In one, we just watch the cells grow happily. Healthy, beautiful cells. Whereas the cells that have the unfolded protein response induced commit suicide and die by having too many unfolded proteins and not being able to fix the problem. Our main discovery is to find out what is the machinery that senses what's going on, whether the system is in equilibrium, whether the ER can handle the load of proteins entering it. Can I fix the problem, or should I rather die? And this sensing machinery is what we discovered. This molecule is called IAU1. It sits in the membrane of the endoplasmic reticulum. So you see the groove in the middle here, the binding site that sees the unfolded proteins. It senses how much unfolded protein do we have. We can watch it in the microscope, and you see that the IAU1 molecules start running together, forming these clusters in the membrane.
Peter believes the ER holds the key to curing cancer.
In cancer cells, for example, we would like to make the unfolded protein response more responsive to unfolded proteins, which are there in the cancer cells, that it will activate a suicide program. That should be very broadly applicable to many different cancers.
That includes the cancer that struck Peter 5 years ago, now in remission.
I came home from a meeting in Europe one day, and Patricia gave me a hug and found this little bump on my neck. And a couple of days later, I had a diagnosis. There was a neck cancer.
He's very strong and with a long will to get well, and we went through.
Patricia is a retired science teacher.
We met in 1980. I had just moved recently to New York City.
At the time, Peter had just received his doctorate from New York's Rockefeller University.
He looked like a caveman.
Yeah, would you date a guy like that?
I am from Mexico, and I came as a graduate student here to the United States. I study in NYU. I got my PhD there. We have two girls, Sylvia and Gabriela.
So it used to be our garage. Now it's my workshop. This is a sculpture I'm making for the garden. It's going to be a fountain. I actually keep very few of the pieces I make. Most of them I give away as gifts to other people. It's the act of making. The same as it is the act of discovering. It's not the discovery in the end that makes me happy, but it's the process of creating these pieces.
Peter grew up in Berlin.
My dad had a little chemist shop in Berlin. So he was selling chemicals and household items. And I became fascinated with chemistry.
He majored in chemistry in Free University in Berlin and took his master's at Vanderbilt in the US.
Oh, Peter! Good to see you, man. Glad to see you. So,
Peter, everyone knows, is probably one of the world's best experimentalists. He's got an amazing talent to going into a problem, an unknown problem, finding exactly the right experiment to do and doing it beautifully. Then when he gets results and extracts gold out of it.
So what about inherited protein folding disease?
1990 is when I started in Peter's lab.
That influence the death pathway.
You choose the lab that you want to do your PhD thesis in. And my roommate got these pamphlets and we went flipping through, and when we got to Peter's, we just laughed. It was like, but there's no way I'd work for him. Here's this guy with all this facial hair, and he was holding a little mouse, and he didn't even work at mice at the time. The two of us said, oh, we'll never, ever join Peter's lab, and blah, blah, blah. But we rotated in his lab at the same time, because we were so compelled by the great science and what an awesome person Peter is.
Peter published his discovery in 1993, the same year as biochemistry professor Kazutoshi Mori of Kyoto University.
It's a severe competition, like a patent.
Mori was in his mid-30s at the time, postdoctoral researcher at the University of Texas Southwestern Medical Center in Dallas. In the early 1990s, scientists were racing to be first to figure out a signaling system that's already been predicted in the endoplasmic reticulum.
I didn't feel good, very tired, and always threatened by the competition. We had another competitor at Princeton University. If he got gene earlier, we lose everything.
Mori took a year to find the IRE1 molecule. He had set up 100,000 yeast cells to identify and isolate mutant ones. If cells turned white, they're mutants whose ER is not firing signals to the nucleus.
I finally got 3 white cells among 100,000 yeast cells, blue cells.
Then came the hard part that took another half year.
I need to get gene which is able to cure these white cells.
This time, Mori tweaked mutant cells with promoter elements, specific DNA sequences of yeast genes, to cure the mutation.
It was a very difficult job. It didn't work well. I was so frustrated, but finally, the system worked. Blue cell means that its mutation is cured. Finally, I found a very small cell. Maybe this is it, I thought. Then I checked it, and then it has a gene. It's IRE1. I told my bosses, I got it.
Mori lives with his wife and 3 kids in Kyoto.
I was born in 1958, small town facing the Seto Inland Sea. My father worked at the automobile company, and my mother and my grandparents are producing agricultural food. There are no atmosphere of science in my family, but I wanted to be a PhD scientist from childhood.
Inspired by his favorite comic heroes.
Mighty Atom, it's called Astro Boy in the American movie. My family is not rich, but my parents worked hard and allowed me to go to school for as long as I wished.
Mori majored in biochemistry and got his master's degree at Kyoto University under one of his mentors.
He is very exceptional. What he did was always perfect, so very impressive.
Mori was among the students Kyoto University had sent to Texas University for their doctorates.
We sent not so many, but maybe 10 students in the United States, but he is the most, of course, successful.
After his breakthrough discovery, he worked for the HSP Research Institute in 1994. Dr. Takashi Yura headed the institute at the time.
We, of course, immediately decided to take him. For us, his research is very closely related to what our institute was aiming for. Good scientist, creative mind.
Mori also teaches kendo to children.
I started when I was 12 years old, for now 44 years. Because I'm not tall, I'm short. But in the kendo, height is not big deal. Once kendo started, it's a one-to-one. If you have to do attack very positively in the kendo, kendo is the basis of my life.
The same martial spirit he brings to science to find a cure for one of the deadliest diseases that has stalked his family.
My grandmother brought diabetes into my family. So my grandmother died with diabetes, and my father suffered from diabetes. He injects insulin every after meal. To avoid diabetes, I have to maintain this body weight. I started biking 2007 to go to school. It's a 10 kilometers, 6 miles one way.
Mori's discovery of the UPR's signaling pathway has opened a new way to combat diabetes. Not by inducing cells to self-destruct, but by making the endoplasmic reticulum more efficient in folding proteins like insulin, which the body must keep producing to keep blood sugar down.
For example, insulin is a string when newly synthesized, but it must be folded. If insulin cannot be folded, it cannot bind to the receptor. That means you cannot decrease blood glucose level. That means that such person will eventually suffer from diabetes. Probably will become able to cure disease with this UPR mechanism, but still we need to do more research because we don't know many things. What kind of protein is misfolded under what kind of situation?
A long quest for an end to diseases that this annual festival celebrates in Kyoto.
It started a long time ago, probably 500 years ago. There's a lot of disease and wars, and so people wanted to have something to pray to cure disease.
A prayer Mori takes to heart.
I always do my best.
Massachusetts Institute of Technology in Boston, and Professor George Lustig, a 2014 Shaw Prize laureate for mathematics. George is honored for his work on representation theory, a branch of mathematics that involves the study of symmetry in groups using matrices.
The more symmetry something has, the more beautiful it is. For example, human face is beautiful if it has perfectly symmetric.
The symmetries of these icosahedron objects are one such group.
They are so complicated that mathematicians view them from many different sides. Take like many X-rays of the group. These X-rays are called representations of the group. Each element of a group is represented by a matrix. The matrices are themselves form a group, and that is better understood than the general group. And so you're trying to understand the general group by representing it by matrices. That's what representation theory is about. It seems to have application to physics. People in elementary particles, they use some of the results that we have in representation theory. And also relevant for number theory. Also cryptography.
George was born in the town of Timisoara in western Romania during the communist era.
I had a happy childhood, I would say, but quite poor. If I needed a winter coat, my parents couldn't buy a winter coat. They had to use some old winter coat and just turn it over, and then make a new coat from old coat.
When he was 12, he started competing in local Olympiads for mathematics. They fascinated him.
There was some kind of mathematical magazine for high school children, and you were supposed to solve problems every month. And I started to spend a lot of time doing that, so maybe 4 hours or 5 hours a day.
In the early 1960s, George, a teenager, won a silver prize twice in the International Math Olympiad.
That sort of convinced me that I should become a mathematician. Well, I think it's the most beautiful activity that I can imagine. It's a thing which gives me most pleasure.
He graduated from the University of Bucharest in 1968.
I was 22 years old. All graduates in mathematics were supposed to go to one place where jobs were assigned to you, according to your grades. So there were, I don't know, 200, 300 people, and I was number one in this set of people, and they didn't want to give me a job. And I learned it because I'm Jewish. I was discriminated in that way.
The jobs he wanted in a university or a math institute were all outside his hometown.
I don't have, this identity card, which in China is called hukou.
Permit to allow him to work outside his town.
So only time you can move is if you get a waiver. So for various other people, this waiver was granted. In my case, there's no waiver. So using that argument, they said that I cannot get a job. So they offered me a job in high school, as a high school teacher.
He ended up teaching at the University of Timișoara in his hometown. That made him realize he had no future in Romania.
I knew that I have to leave at the first opportunity.
In 1969, 1 year after graduation, George was allowed to join a conference in Bonn in Germany. He never returned to Romania. He applied and got accepted into Princeton University, where he obtained a master's degree and a doctorate in the early 1970s. He joined the University of Warwick in Britain in the mid-1970s as a lecturer, then as a professor 3 years later. He moved to MIT in 1978.
I know that I was convicted of leaving the country illegally, and this I know because at some point I applied to Romanian embassy to renounce the Romanian citizenship. I wanted not to have it anymore, and they told me that you can only do that after you do your jail sentence.
George became a British citizen while working in England. He wrote 5 books about mathematics, 3 of them on representation theory.
Certainly not for lay people. It's exhausting. It's very, very hard. In particular, this book, I almost got sick. Introduction to Quantum Groups.
A book he had written while working on a joint academic paper with a colleague and teaching a class.
I was overworked, and my health was not good. I thought that maybe if I do yoga, this will be helpful for me, and went to a class, and I found indeed that it's very, very helpful. Improved my health, for example. You learn to focus on things. I become vegetarian. That's also part doing yoga.
He lives with his wife Gong Chin in Boston.
He's a nice, you can see through the eyes, he's a nice person and intelligent.
Gong Chin was born in mainland China. She works as a software developer in MIT and has a doctorate in mathematics.
She has some experience how a mathematician thinks. I think it's very difficult for women to marry a mathematician, because mathematicians always think of something else, always in different worlds.
He works at home all the time. I'm fine with that. That's the nature of being a mathematician. You keep thinking problems, sometimes you don't want to actually interrupt. Also, so I was trained as a mathematician also. I know this kind of things.
And interesting. I'm constantly overwhelmed by him.
David Vaughan Jr., a mathematician from MIT.
There are a lot of really basic problems in the field which sort of appeared to be impossible to solve, and he solved a lot of them. He just brought completely new ideas in and just changed the way everyone thinks about the field.
Well, the same as a good chess player, how many moves he can see in advance. So it's the same in mathematics. And seeing many moves in advance meaning having a good intuition. And that makes a good mathematician.